Chapter 3, Matter and Energy. Let's jump into this thing. So, first question we need to ask is, what's the matter? No, that's not the question. What is matter? If we're going to study matter and energy, we should probably understand what those two things are. So we're going to start here with matter. Matter is defined as anything that has mass and takes up space or has volume. That is the most common definition anyway. You can find other ones that are pretty much the same but slightly different online, but this is the most common definition for matter. And what this is telling us is that essentially matter is nearly everything in the universe. There are a few things that technically do not have mass or take up space. Photons, for example, sometimes don't have mass. And most of the time, actually, they behave like they have mass sometimes. It's complicated. But the vast majority of everything that you ever interact with in your life is made up of matter. So water, your chair that you're sitting on, the air that you're breathing, all of that stuff has mass and takes up space. If we want to classify matter with a little bit more specificity, we don't just want to say everything in the universe, that's matter. If we want to actually categorize it a little bit, there's a few different ways we can do that, split matter up into groups, so to speak. One of the main ways to do that is to split it up into the phase of matter that you're looking at. And there are three of these main physical states of matter. There is a fourth one that you don't really hear about very much, but it is actually very common, mainly because stars are made of it, which we will, let me see, do we talk about that later? Yeah, we do talk about it a little bit later. So that's plasma as well, but the three main physical states of matter are solids, liquids, and gases. So if we're looking at a solid, which you are very familiar with, these have rigid shapes and fixed volumes, which is essentially saying that you can't take a solid and stretch it out to be a larger size. If you have, a piece of paper next to you right now and you grab that piece of paper and you try to stretch it to make it occupy a larger volume, it's not going to work. It's just going to rip. Solids have rigid shapes and fixed volumes. Now you can change those shapes, you can force them to be into a different shape, then now they have a new rigid shape. The atoms in these types of materials, in solids, are bound to fixed locations, which means that they're not moving around, they're not going from one place to another, they're stuck, in a sense, in the solid where they are. There are two different types of these solids in terms of the way that the atoms are arranged. There are crystalline solids and there are amorphous solids. And the difference between these is how ordered the atoms are in the solid itself. So crystalline solids, they are very ordered. There's a long-term structure to the atoms. So metals are generally what we would consider crystalline. There are certain plastics that are crystalline and certain plastics that are amorphous. The main thing that we're looking for here with a crystalline structure is just that there's a very well-structured order for the atoms themselves. There's a place for everything, and everything is in its place, so to speak. While amorphous solids, there is no long-term order. Everything's just kind of a big jumbled mess. Like everything is still stuck where it is, but if you look at one place in the structure and you look at a different place in the structure, they're going to look very different. It's not going to have the exact same structure. So most plastics that are clear are amorphous. plastics. They are amorphous solids. Liquids, on the other hand, have an indefinite shape and a fixed volume. So they're still similar to solids in that the volume that they occupy is still fixed, but they are different because now their shape is no longer rigid. They're not limited to just one shape. So you have some liquid in this container here, and it has a certain shape, but if you were to tip this this container over, not so much that it spills out, but just on its side a little bit, well, now the liquid would have a different shape. It just follows the shape of the container that it's in. Liquids always assume the shape of their container. They do not assume the size of the container. They don't occupy the full container unless they just happen to match whatever the volume of the container is. But they do take the shape of the container. The atoms in a liquid are still really close together, like they would be in a solid. They're not really far apart, and in some cases they're actually closer to each other than they are in the solid phase. But they are moving around freely, which is what gives liquid the ability to flow like it does, because the molecules or the atoms are not held in a single place. They can freely move, they can bump into each other and kind of hop over each other, and they're moving around independent to one another. Gases are going to take that to the extreme. Gases, not only are the atoms free to move around as much as they want, but they're not close together anymore. The molecules are, atoms or molecules are very separated, which gives gases an indefinite shape and an indefinite volume. So if you take a sample of gas and you put it into a space that is unoccupied, so there's nothing else, there's a vacuum in that space, and you put a little bit of gas into that space, the gas is going to expand and completely fill that container. Now, it might not fill it enough to where you could breathe the gas in there. It could be very, very thin gas, but it would still fill to fill the container. That's what gases do. They just expand, they just move around, and they just move freely, and they fill whatever container they're in. They're also very compressible compared to other phases of matter. So liquids and solids, I don't know if you've ever tried this, and I would not encourage you to. Because it just end up hurting yourself. But if you have ever tried to take a 2 liter, for example, that's full of water, and you try to compress the water, either by just pushing on it or jumping on it or something, again, do not try this at home. You will end up falling and hurting yourself. The liquid water doesn't compress at all. You cannot compress a 2 liter that is full of water. If you take a quote empty 2 liter, it's not actually empty because it has atmosphere in it, it has gas in it, and you try to compress that, well, that compresses fairly easily. Gases you can compress, liquids and solids not so much. And then the last phase of matter here that we mentioned just a minute ago is the plasma phase. You don't really see this very often mentioned in books because there's not a whole lot of plasma on planet Earth. There is some, and we use it for very cool and interesting things like plasma cutters. Plasma cutters do actually use a plasma to cut things, as the name implies. But what a plasma is it is the fourth state of matter. If you keep heating a gas up, then it will eventually turn into a plasma, which is an ionized, very high temperature gas, which is still not a great way of describing it. That's like saying a gas is a hot liquid, but it's the best I can do, because we don't interact with plasmas really, it's difficult to really grasp what they are. But they are very, very hot, thousands of degrees Celsius, and they are the most common phase of matter in the universe, actually, because stars are made of plasma. And lightning as well is plasma, which, since you live here in Oklahoma, you are quite familiar with lightning. Hopefully not on a personal basis. Hopefully none of you have been struck by lightning before. But I'm sure you have at least seen it. And what lightning is actually when that very high energy electrical discharge happens in the atmosphere. Where the discharge occurs, because it's so high energy, it heats the atmosphere up to the point where the atmosphere actually turns to a plasma and gives off light. And so what you're seeing is actually the atmosphere. You're not actually seeing the electricity, so to speak. You're actually seeing the effect of the electricity turning the atmosphere to plasma for a split second before it cools down again through giving off that light. So we'll call it there for this video, and the next one we will talk about classifying matter based on its composition. So I'll see you there.